On a clear night, away from the light of cities, the stars appear close. This is an illusion, one of the deepest and most persistent illusions available to human perception. The stars appear close because they appear at all, because they are bright enough to see, because the eye cannot measure depth across such distances, because the sky presents them all on the same flat dome of darkness, regardless of whether they are 40 light years away or 40,000. They look near, they look like they could be reached, they cannot. The nearest star to our Sun, Proxima Centauri, a small dim red dwarf orbiting in the southern constellation Centaurus, is approximately 4.24 light years away. 4.24 light years. When you hear that number, something in the mind accepts it without truly confronting what it means. 4.24 light years. A number with a decimal point, tidy, expressible in a single breath. But 4.24 light years is approximately 40 trillion kilometers. 40 trillion. A 4 followed by 13 zeros. And that distance, that extraordinary, almost incomprehensible span, is not the distance to a far galaxy, not the distance to a remote cluster of stars, not the distance to some exotic object at the edge of the observable universe. It is the distance to our nearest neighbor, the next door, the closest thing to our solar system that the cosmos contains. Tonight, we are going to sit with that distance, not skim past it, not allow the mind to absorb the words and move on without truly registering what they describe. We are going to trace what 40 trillion kilometers actually means, in human terms, in spacecraft terms, in physics terms, in the terms of every comparison that might make the scale begin to feel as large as it actually is. Because the distance between here and the nearest star is not merely large. It is a different category of large from anything that ordinary human experience contains, and understanding that difference, truly feeling, even momentarily, the scale of what separates us from even our closest stellar neighbor, is one of the most clarifying, and in a strange way, most peaceful experiences that contemplating the cosmos can provide. This is not a journey of despair. The distance is vast, and it will remain vast, but there is something genuinely worth knowing in understanding why it is so vast, and what that vastness means. The universe is not made incorrectly. Its scale is not a mistake or a cruelty. It is simply what the universe is, operating at scales that our evolutionary history gave us no preparation to intuit. Tonight we learn to intuit it, slowly, together. If you love exploring the cosmos, a like and subscribe would mean the world to us. Let's begin. Light travels at approximately 299,792 kilometers per second. This is not merely a fast speed. It is, as far as physics can determine, the absolute maximum velocity at which any information, any signal, any physical object with mass can travel through the universe. Not a limit imposed by current technology, a fundamental limit built into the structure of space-time itself, arising from the mathematics of Einstein's special theory of relativity, and confirmed by every experiment ever conducted to test it. At this velocity, nearly 300,000 kilometers per second, light behaves in ways that defy ordinary intuition. It circles the entire Earth approximately 7.5 times in 1 second. It travels from the Moon to Earth in approximately 1.3 seconds. It crosses the average distance from Earth to the Sun, 150 million kilometers, in approximately 8 minutes and 20 seconds. Light time, the time light takes to cross a given distance, is the natural language of cosmic distances. When we say that the Sun is 8 light minutes away, we mean that the sunlight illuminating this moment left the Sun 8 minutes ago. When we say that the Moon is 1.3 light seconds away, we mean that the moonlight visible on a clear night left the Moon's surface 1.3 seconds before it reached our eyes. These are intimate distances by cosmic standards. The light minute and the light second are units appropriate for the solar system. For the distances between planets and their moons, between the inner planets and the outer ones. For interstellar distances, a new unit is needed, the light year. The distance light travels in 1 year, moving at its maximum velocity without pause or interruption across empty space. 1 light year is approximately 9.46 trillion kilometers. 9,460 billion kilometers. That is the distance light covers in a single year of continuous travel. Proxima Centauri, the nearest star, is 4.24 light years away. The light leaving Proxima right now will take 4 years, 2 months, and several days to reach Earth. The light we observe from Proxima tonight left that star in approximately the year 2021 or 2022, before many of the events of recent years had occurred. We are seeing the past. We are always seeing the past when we look at the stars. And 4 light years, this apparently small number, translates to approximately 40 trillion kilometers, 40,000 billion kilometers, a distance so large that no comparison drawn from human experience fully captures it. We will try several comparisons. We will fail, as all such comparisons fail when the scale is truly cosmic. But the attempt is worth making. Each failure to capture the scale is, in its own way, a lesson in how large the universe actually is. The history of attempts to communicate the scale of interstellar distances is a history of comparisons that almost work, that gesture toward the truth without fully grasping it. Let us try several, not because any will succeed, but because each one moves the mind a little further toward genuine comprehension. Attempt 1. The fastest spacecraft humanity has ever built, New Horizons, launched in January 2006, traveled at approximately 58,000 kilometers per hour relative to Earth when it was given its final gravity assist from Jupiter. This was the highest speed ever achieved by a human-made object, propelled by the most powerful rockets available, and augmented by the gravitational pull of the solar system's largest planet. At this velocity, how long would New Horizons take to reach Proxima Centauri? The answer is approximately 78,000 years. 78,000 years. Modern Homo sapiens has existed for approximately 300,000 years. The entire span of recorded human history, from the first written languages to the present, is approximately 5,000 years. New Horizons, at the highest speed humanity has yet achieved in space, would not reach the nearest star before our species has lived through 17 times the span of all recorded history. Attempt 2. Scaling the solar system. Imagine the solar system scaled so that the sun is the size of a grapefruit, about 10 centimeters across. At this scale, Earth orbits approximately 11 meters from the grapefruit sun. Neptune, the outermost planet, orbits approximately 330 meters away. The entire solar system, including the Oort cloud at its most distant, extends to perhaps 100 kilometers. At this scale, Proxima Centauri is approximately 2,800 kilometers away, about the distance from New York to Denver, or from London to Moscow, a journey you could make in a few hours by aircraft. But at this scale, your aircraft would be traveling through empty space, because at these scales, the interstellar medium contains essentially nothing. No air, no molecules, nothing to navigate by, nothing to see, nothing to slow you down or help you along. Attempt 3. Driving at highway speed. If you could drive to Proxima Centauri at highway speed, 100 kilometers per hour continuously, without stopping, the journey would take approximately 46 billion years. The universe is only 13.8 billion years old. Each of these comparisons fails, because each of them eventually reaches a human reference. 78,000 years. New York to Denver, 46 billion years. That is itself not intuitively graspable. The mind accepts the words without truly feeling the scale. This is not a failure of imagination. It is an honest acknowledgement of the limits of a mind evolved to navigate a world where the largest distances are measured in thousands of kilometers and the longest timescales in decades. The scale of interstellar distance is simply, genuinely, beyond ordinary human intuition. Understanding this is itself a kind of understanding. The question deserves to be asked directly. Why are the stars so far apart? Is this a coincidence of our particular cosmic neighborhood? Is it a universal feature? And what physical principles determine the typical distance between stars? The answer involves stellar formation physics, the processes by which stars condense from clouds of gas and dust, and it turns out to be deeply connected to the very fact that stars can exist at all. Stars form when regions of molecular clouds, the vast, cold, diffuse clouds of hydrogen and helium that populate the interstellar medium, become dense enough for gravity to overcome the thermal pressure that otherwise prevents collapse. The density threshold for star formation is set by the interplay between gravity and thermal energy, and the result, the typical mass of a forming star, is set by the properties of hydrogen and helium gas under the conditions found in molecular clouds. The typical distance between stars in a galaxy like the Milky Way, a few light years in the solar neighborhood, is set by the combination of the stillus formation process and the equilibrium dynamics of the galactic disk. Stars form in clusters from molecular clouds, but after formation, they gradually disperse through the galaxy over hundreds of millions of years, reaching the relatively uniform distribution we observe today. The specific separation between stars is not arbitrary. It reflects the mass of stars, the velocity dispersion of stellar populations, and the overall mass distribution of the galaxy. In more massive galaxies, stars are denser on average. In less massive ones, sparser. The Milky Way's specific size and mass produce the specific density of stars in the solar neighborhood. Approximately 1 star per 4 or 5 cubic light years. There is also a more fundamental reason why stellar separations must be large. The energy output of a star, the luminosity, depends on its mass in a steeply nonlinear way. More massive stars are exponentially more luminous. A star only slightly more massive than the Sun produces vastly more radiation. If stars were packed closer together, their mutual radiation would heat the surrounding gas to temperatures that prevent new star formation, and that would make planetary systems far more hostile to complex chemistry. The distances between stars are therefore not merely a coincidence of our location or our epoch. They reflect fundamental physics, the properties of hydrogen, the nature of nuclear fusion, the relationship between stellar mass and luminosity, the dynamics of galactic structure. A universe with the same physics as ours, but with stars much closer together, would not be a friendlier universe for life. It might not be a universe capable of supporting complex chemistry at all. The vast distances between stars are, in a specific physical sense, a prerequisite for the existence of stable, long-lived stars with stable planetary systems in which complex chemistry can develop. The emptiness between the stars is not a failure of cosmic generosity. It is a structural feature of a universe capable of producing the conditions for biology. The 40 trillion kilometers between here and Proxima Centauri is not nothing. Empty space, in the physicist's sense, is never truly empty. The region between stars, called the interstellar medium, contains matter, energy, and fields, though at densities so low they are essentially incomprehensible to ordinary experience. The interstellar medium has multiple components, each with different physical properties and different origins. The most abundant component is neutral hydrogen gas. Individual hydrogen atoms, drifting through space at temperatures ranging from roughly 10 Kelvin in the coldest densest molecular clouds to tens of thousands of Kelvin in the hot ionized regions near young stars. The density of this hydrogen gas is extraordinarily low, typically approximately 1 atom per cubic centimeter in the warm, neutral medium that occupies most of the volume of the galactic disk. A cubic centimeter is roughly the volume of a sugar cube, 1 atom per sugar cube volume. Compare this to air at sea level, which contains approximately 27 trillion molecules per cubic centimeter, and you begin to appreciate the scale of the emptiness. Molecular hydrogen, hydrogen atoms paired into H2 molecules, is found in the cold, dense molecular clouds where star formation occurs. These clouds can be thousands of light years across, but occupy a small fraction of the total volume of the galactic disk. Dust, microscopic solid grains of silicate and carbonaceous material, pervades the interstellar medium, though at extraordinarily low densities. The dust grains are typically less than a micrometer in size. They absorb and scatter light, causing the reddening of distant stars that astronomers must account for in their observations. Despite their low density, interstellar dust grains are cosmically important. Their surfaces catalyze chemical reactions that could not occur in the gas phase, producing complex molecules including many relevant to prebiotic chemistry. Cosmic rays, high-energy charged particles, primarily protons and heavier atomic nuclei, accelerated by supernova remnants and other energetic astrophysical events, permeate the interstellar medium at relatively uniform density. They carry enormous individual energies, some orders of magnitude beyond what any terrestrial particle accelerator can produce. They are a significant radiation hazard for any spacecraft attempting interstellar travel. The interstellar magnetic field, produced by the collective motion of charged particles in the galaxy, threads through the interstellar medium at field strengths of a few microgauss. Weak by any ordinary standard, but capable of influencing the trajectories of cosmic ray particles and the dynamics of molecular cloud collapse. And then there is the cosmic microwave background, the faint thermal radiation left over from the Big Bang, filling all of space at a temperature of approximately 2.7 Kelvin. Even in the deepest void between galaxies, the universe is not at absolute zero. It glows faintly with this ancient heat. The space between stars is not nothing. It is extraordinarily thin, extraordinarily cold, extraordinarily empty by the standards of any planetary environment. But it is a medium, a physical environment with properties that a spacecraft attempting interstellar travel must navigate. Imagine, for a moment, that you are aboard a spacecraft making the crossing from a solar system to Proxima Centauri. Not the engineering details of how such a spacecraft would be built or powered we will address this as elsewhere, simply the experience, what the journey would be like. The first months of the journey would involve leaving the solar system, passing through the inner solar system, where the planets orbit, crossing the asteroid belt, climbing outward past Jupiter's enormous presence, past Saturn's ringed majesty, past the ice giants Uranus and Neptune. Throughout this phase, the sun remains the dominant object in the sky, brilliant, warming, the center of still recognizable family of worlds. Beyond Neptune's orbit, the solar system continues, but the density of objects thins dramatically. The Kuiper Belt, a region of icy bodies extending roughly from 30 to 50 astronomical units, is crossed. Then, the spacecraft enters the scattered disk and the heliosheath, the outermost regions of the solar wind's influence. The sun has diminished from its familiar brilliance to a very bright star, still the brightest object in the sky by far, but no longer a source of illumination sufficient to warm a planetary surface. At approximately 100 astronomical units, roughly 100 times the Earth-Sun distance, the spacecraft crosses the heliopause. The solar wind, which has been flowing outward, and defining a bubble of solar influence through the entire solar system, finally loses its battle against the pressure of the interstellar medium. The spacecraft enters interstellar space. The sun is now a bright star among stars, brilliant, the brightest point in the sky, but a point, not a disk. Its warmth is negligible at this distance. The spacecraft, if it carries humans, must be self-sufficient for heat. The sky in all directions is filled with stars, but they are fixed, not moving, not changing in any way detectable within a human lifetime. The journey is measured not in visible progress, but in the instruments. The radio signals timing the spacecraft's distance from Earth, the spectrographic measurements of the interstellar medium flowing past, the faint proper motion of Proxima Centauri, gradually growing slightly less faint as the decades pass. The interstellar medium flowing past at the spacecraft's velocity is extraordinarily thin, at 1% of the speed of light, already a velocity far beyond anything humanity has achieved. The hydrogen density is so low that impacting atoms represent no meaningful structural hazard. But at higher velocities, even the thin interstellar medium becomes a hazard. Particles impacting a spacecraft at significant fractions of the speed of light carry real kinetic energy and can damage unshielded surfaces over time. And the silence. Not acoustic silence. Space is already acoustically silent. A deeper silence. The absence of any signal from home that has not already aged by years. The absence of any ability to call for help and receive it in time to matter. The genuinely new silence of a vessel far from any source of assistance in the vastest ocean that the physics of our universe allows. This would be the crossing. Not dramatic, not filled with passing objects. Simply the slow, relentless, patient advance through the thinnest environment the universe contains, toward a point of light that would, after years of travel, very gradually resolve from a point to something that might be imagined as a destination. The distance between stars is the fundamental obstacle, but it is not the only obstacle. The environment of interstellar space presents specific hazards that any spacecraft or living crew would need to contend with, and understanding them clarifies why interstellar travel is not merely an engineering problem but a challenge that touches the deepest limits of what physics allows. Radiation is perhaps the most insidious. Galactic cosmic rays, those high-energy particles accelerated by supernovae throughout the galaxy, permeate all of space, including the region between stars. Within the heliosphere, the solar wind provides some partial shielding, deflecting lower energy cosmic rays and reducing the flux reaching the inner solar system. In interstellar space, this shielding is gone. The flux of galactic cosmic rays in the interstellar medium is approximately 2 to 3 times higher than in the vicinity of Earth. For a human crew on a long interstellar voyage, the accumulated radiation dose would be substantial. Current NASA limits for astronaut career radiation exposure, set at the dose associated with a 3% increase in lifetime cancer risk, would be exceeded within a few years of travel in the interstellar medium without shielding. Passive shielding is problematic for the most energetic cosmic ray particles. When a very high-energy proton or heavier nucleus strikes a dense shielding material, it can produce secondary radiation, showers of secondary particles that can actually increase the biological dose behind thick shielding of the wrong type. The optimal shielding involves hydrogen-rich materials, water, polyethylene, that absorb the primary particles efficiently without excessive secondary production. A water shield of 1 to 2 meters surrounding the crew habitat would reduce but not eliminate the cosmic ray dose. At high velocities, the interstellar medium itself becomes a hazard. Dust grains, even at the extraordinarily low densities of the interstellar medium, carry significant kinetic energy when a spacecraft moves at a meaningful fraction of the speed of light. A dust grain of 1 microgram, impacting a surface at 10% of the speed of light, carries the energy of a rifle bullet. At 1% of the speed of light, the energy is smaller but still significant over an extended voyage. The leading surfaces of any high-velocity interstellar spacecraft must be designed to withstand this continuous bombardment, or the spacecraft must carry a shield, a sacrificial structure at the bow that absorbs impacts and protects the main vessel behind it. Interstellar neutral hydrogen, 1 atom per cubic centimeter, flowing into the spacecraft at high velocity, also represents a hazard. At 1% of the speed of light, hydrogen atoms have energies comparable to low-energy protons in a particle accelerator. Over the course of a multi-decade voyage, the total dose from interstellar hydrogen impacts on the leading surfaces of an unshielded vessel would be significant. These hazards are not insurmountable in principle. They point toward specific engineering solutions, not physical impossibilities. But they add to the already enormous challenge of crossing the interstellar medium, reminding us that the space between stars is not merely empty and cold and vast. It is an environment with its own specific hostilities. The fundamental obstacle to interstellar travel, beyond the distance itself, is the physics of propulsion, and this physics is governed by a deceptively simple equation, the Tsiolkovsky rocket equation, that places severe constraints on what conventional rocket technology can achieve. The rocket equation says that the velocity change a rocket can achieve depends on 2 things: the exhaust velocity of its propellant and the ratio of initial mass to final mass. For a rocket that starts at a certain total mass, struck, payload, and fuel, and burns its fuel to accelerate, the final velocity depends logarithmically on the mass ratio. Double the fuel to payload ratio, and you get only a modest increase in final velocity. To achieve 10 times the exhaust velocity of the propellant, you need to start with approximately 22,000 times as much propellant as final payload. The math is unforgiving. Chemical rockets, which power all current spacecraft, achieve exhaust velocities of roughly 2 to 4 kilometers per second for the most energetic chemical reactions. At this exhaust velocity, achieving a significant fraction of the speed of light is essentially impossible. The required fuel-to-payload mass ratio becomes astronomical, far beyond any conceivable engineering. Nuclear thermal propulsion, which heats propellant with a nuclear reactor to increase exhaust velocity, can achieve velocities of roughly 8 to 10 kilometers per second. Better, but still far short of what interstellar travel demands. Nuclear pulse propulsion, the concept explored in the late 1950s and early 1960s under the names Project Orion and Project Daedalus, is more promising. By detonating a series of small nuclear explosions behind the spacecraft and using the blast pressure against a pusher plate, theoretical designs suggest velocities of several percent of the speed of light might be achievable. With fission or fusion fuel, at 3 to 5% of the speed of light, the journey to Proxima Centauri would take approximately 85 to 140 years. Long but not millennia. Antimatter propulsion is theoretically the most efficient rocket propulsion possible. When matter and antimatter annihilate, they convert their entire mass to energy, the most energy-dense reaction conceivable in ordinary physics. An antimatter rocket could, in principle, achieve a significant fraction of the speed of light with a mass ratio that is physically achievable. The obstacles are entirely practical. Antimatter is extraordinarily expensive to produce, cannot be stored for long without careful magnetic containment, and the technology for an antimatter drive does not exist in any demonstrated form. Laser sail concepts, accelerating an extremely thin, reflective sail with a powerful laser beam, sidestep the rocket equation entirely. The laser remains behind. Only the sail and its small payload are accelerated. The Breakthrough Starshot Initiative has proposed accelerating gram-scale probes to 20% of the speed of light, with a large ground-based laser array. At this velocity, the journey to Proxima Centauri would take approximately 20 years. The challenges are engineering, maintaining a precisely focused laser beam over the acceleration distance, constructing a sail that can withstand the laser power without being destroyed, and transmitting data back from a tiny probe, traveling at a fifth the speed of light. Each of these approaches faces different combinations of physical constraints and engineering challenges. None is currently deployable, but none violates known physics. The question is whether any civilization will ever find the will and the resources to build the required systems. There is one feature of physics that at first glance appears to offer relief from the challenge of interstellar distances. It is time dilation, one of the most counterintuitive predictions of Einstein's special theory of relativity, confirmed by experiments and observations in multiple contexts. As an object moves faster, as it approaches a significant fraction of the speed of light, time passes more slowly for that object relative to stationary observers. A clock aboard a spacecraft moving at 90% of the speed of light runs slower than a clock on Earth by a factor of approximately 2.3. A clock at 99% of the speed of light runs slower by a factor of approximately 7. At 99.9% of the speed of light, the factor is approximately 22. For an astronaut aboard such a spacecraft, the journey to Proxima Centauri at 99% of the speed of light would take approximately 4.3 years as measured in Earth's reference frame, but only about 7 months as experienced by the traveler. At 99.9% of the speed of light, the subjective journey time would be only about 2.5 months, while 4.3 years pass on Earth. This seems to offer hope. If the traveler can tolerate the subjective journey time, which might be months or years at sufficiently high velocities, then even interstellar distances become traversable within a human lifetime. But the relief is incomplete for several reasons. First, reaching 99% of the speed of light requires extraordinary energy. The kinetic energy of even a 1 kilogram mass at 99% of the speed of light is approximately 500 times its rest mass energy, equivalent to the explosion of approximately 7,000 nuclear warheads. For a spacecraft of reasonable mass, the energy required is genuinely astronomical by any current technological standard. Second, deceleration at the destination requires the same energy investment as acceleration. A one-way flyby at near light speed produces a traveler who spends months experiencing the journey, but arrives with no ability to slow down. A crewed mission that intends to land, explore, and potentially return must accelerate and decelerate twice. For energy-intensive, staggering cost. Third, the time dilation that benefits the traveler is a source of profound disconnection from the origin civilization. An astronaut who departs at near light speed and returns after a journey that took 20 years on Earth, but only 2 years subjectively has, from Earth's perspective, been gone for 20 years. Everyone they knew has aged. The civilization they left has changed. The communication delay during the journey meant that real-time connection was impossible. Time dilation does not solve the problem of separation. It transforms it into a different kind of separation between the traveler's subjective experience and the objective passage of time in the universe they are traveling through. The most persistent hope in discussions of interstellar travel is the possibility of exceeding the speed of light, of finding some loophole in physics that would allow travel faster than the 300,000 kilometers per second that current theory establishes as the universal maximum. The desire for such a loophole is entirely understandable. If you could travel faster than light, the interstellar distances that currently seem prohibitive would become manageable. The 40 trillion kilometers to Proxima Centauri would be crossable in hours or days rather than years or centuries. But the prohibition on faster-than-light travel is not a technological limitation waiting to be overcome. It is a consequence of the mathematical structure of space-time, of the way that space and time are linked in Einstein's special theory of relativity, and the experimental evidence supporting that structure is overwhelming. The key insight is that the speed of light is not merely a speed. It is a property of space-time itself, the exchange rate between space and time in the four-dimensional geometry of the universe. The speed of light appears in the equations of physics, not because light is special, but because light is massless and massless particles travel at the maximum speed that space-time permits. Any particle with mass, no matter how much energy is added to it, can approach but never reach the speed of light, because as its velocity approaches the limit, the energy required to increase its velocity further approaches infinity. This is not a matter of not having enough fuel. Adding more fuel to a spacecraft increases its energy, but as the spacecraft approaches the speed of light, the additional energy goes increasingly into increasing spacecraft's relativistic mass rather than its velocity. The mathematics are unambiguous. Infinite energy would be required to reach the speed of light for any object with mass. Several speculative concepts have been proposed that might circumvent this limit without violating it. The Alcubierre warp drive, a solution to Einstein's field equations proposed in 1994, describes a metric where a bubble of flat spacetime moves through a surrounding region of warped space, carrying a spacecraft inside the bubble faster than light could travel through the surrounding space. The spacecraft inside the bubble is locally at rest. It does not exceed the speed of light within its own reference frame, but the bubble moves faster than light. The problem with the Alcubierre drive is not that it violates the equations of general relativity. It does not, but that its realization requires exotic matter with negative energy density. Such matter may or may not exist in the required form, and no known mechanism for producing it at the required scale has been identified. Furthermore, subsequent analysis has shown that the Alcubierre metric likely requires a total energy comparable to the mass energy of Jupiter, converted entirely to exotic matter. Traversable wormholes, hypothetical shortcuts through space-time that would allow travel between distant points, also appear as solutions to the field equations, but again require exotic matter to remain stable. Whether exotic matter exists in the required form remains an open question in physics. The honest assessment is that no mechanism for circumventing the speed of light limit has been demonstrated to exist, and the proposals that might work require physics that is either not established or not achievable with any understood technology. The speed of light limit is, for all practical purposes that can be engaged with today, real. Despite the formidable obstacles we have traced, the human community of scientists and engineers has developed a number of proposals for interstellar travel, or at least interstellar reconnaissance, that are based on established physics rather than speculative new science. They are difficult. Some are extraordinarily difficult, but they do not require the discovery of new physical laws. The Breakthrough Starshot initiative, announced in 2016 and funded by the late Russian entrepreneur Yuri Milner, proposes sending gram-scale probes, centimeter-scale laser-sail vehicles, to the Alpha Centauri system at 20% of the speed of light, powered by a ground-based or space-based laser array of approximately 100 gigawatts of power. At this velocity, the probes would reach Alpha Centauri in approximately 20 years of travel. They would fly through the system, not stopping, conducting a high-speed reconnaissance, and transmit data back at the speed of light, which would arrive approximately 4 years after the probe's transit. The engineering challenges are substantial. The laser array required does not exist and would require decades to develop. The sail material must reflect the laser light efficiently while withstanding the power density of the beam, approximately 100 gigawatts per square meter, without being destroyed. The probe must be extraordinarily small and lightweight while carrying functional cameras, spectrometers, and communication equipment. The communication system must transmit useful data from a tiny probe traveling at 20% of the speed of light, across 4 light-years to an Earth receiving station. None of these challenges is resolved. Significant research has been conducted on each, with some promising early results in laser technology, sail material science, and miniaturized electronics. But the gap between current demonstration capabilities and the required performance specifications remains large. Nuclear pulse propulsion, the approach most seriously studied in the 20th century, was analyzed in detail by Project Daedalus, a British interplanetary set-aside study conducted between 1973 and 1978. The Daedalus design proposed a 2-stage unmanned probe powered by fusion. Micro-explosions, small pellets of deuterium and helium-3 ignited by electron beam to create tiny nuclear explosions at a rate of approximately 250 per second. The design, after nearly 5 years of study by professional aerospace engineers and physicists, concluded that a vessel of approximately 50,000 tons, most of it fuel, could achieve approximately 12% of the speed of light and reach Barnard's star 6 light-years away in approximately 50 years. The Daedalus study remains one of the most thorough engineering analyses of an interstellar mission concept ever conducted. Its conclusions point to a spacecraft that, while technically feasible in principle, would require manufacturing capabilities far beyond current levels, including the mining of helium-3 from Jupiter's atmosphere, which does not exist as a technical capability today. More recently, the Icarus Interstellar Organization and the Initiative for Interstellar Studies have updated and revised the Daedalus design, producing the Icarus concept with more realistic engineering assumptions and a broader range of fuels. The fundamental conclusion remains: fusion-powered interstellar travel is technically plausible, but requires engineering development measured in decades to centuries. The approaches discussed so far share a common feature. They envision interstellar travel on timescales that might be survived by a single individual or a single spacecraft. 20 years for a laser sail probe, 50 years for a fusion pulse ship. These are long journeys, but they are not inconceivably long in human terms. What if the propulsion challenge cannot be solved at these scales? What if the fastest practical interstellar spacecraft must travel at velocities that produce journey times of centuries? The generation ship concept, explored in detail elsewhere in this series, addresses this by accepting the time scale rather than fighting it. A generation ship would not attempt to get one person to the destination within their lifetime. It would carry a community, perhaps thousands of people, who would live and work and reproduce aboard the ship for the duration of a journey, measured in generations. The founders would never see the destination. Their grandchildren's grandchildren would be the ones to arrive. The generation ship transformed the interstellar journey from a voyage of individual exploration to a project of civilizational transmission. It requires not only the engineering of a self-sustaining habitat across centuries, but the sociology and psychology of maintaining a purposeful community across generations who did not choose to be on the journey. The minimum viable population for a multi-generational voyage, sized to maintain genetic diversity across centuries of closed population reproduction, has been studied by biological anthropologists and geneticists. Estimates range from a few hundred to several thousand individuals, depending on assumptions about breeding programs, stored genetic material, and acceptable levels of genetic drift. The ship must be large enough to house and sustain this community for the journey's duration, potentially centuries. A generation ship traveling at 1% of the speed of light, a velocity that represents a significant engineering challenge, but not an unresolvable one with plausibly advanced propulsion, would take approximately 420 years to reach Proxima Centauri, approximately 17 to 20 generations of people, depending on generational length. The descendants of the founders, separated from Earth by 20 generations of time and 4 light years of space, would be the ones to emerge into the light of a new star. The generation ship is perhaps the most genuinely honest response to interstellar distance, the one that accepts the scale, rather than pretending it can be overcome, and asks instead what kind of human institution could survive that scale intact. There is a conceptually distinct approach to interstellar travel that does not involve moving physical matter, biological or mechanical, across the void. It involves instead transmitting information. Consider what a human being actually is from an information theoretic perspective. A person is, among other things, a specific physical configuration, neurons connected in a specific pattern, memories encoded in synaptic weights, personality expressed in the dynamics of a biological nervous system. If that configuration could be measured with sufficient precision and transmitted as data, if the informational content of a human mind could be encoded and sent, then a person could in principle be transmitted across interstellar distances at the speed of light. Upon arrival at the destination, the transmitted information would be received and used to construct, or to run in simulation, a version of the transmitted individual. Whether this constitutes the same person, or a copy, or something philosophically distinct from either, is a deep and genuinely unresolved question in the philosophy of mind and personal identity. The transmission itself faces profound practical challenges. The number of bits required to encode a human mind, if such encoding is even possible, is not known, but estimates range from approximately 10 to the 23rd to 10 to the 26th bits, depending on assumptions about the relevant level of description. At current data transmission rates, transmitting this quantity of information would take far longer than any practical timescale. Advancing data transmissions technology would need to improve by many orders of magnitude. The question of whether the informational content of a mind can be extracted at all, whether consciousness and subjective experience are computational properties of the information processing, or whether they depend on the specific physical substrate, is not resolved by current neuroscience or philosophy. The digital mind transmission approach assumes that the informational description is sufficient. This assumption may be correct. It may not be. Intermediate approaches, transmitting the information needed to build specific humans in a receiving system with embryo synthesis from transmitted genomic and developmental data, are more tractable than full mind transmission. A laser beam carrying the genetic information of several thousand humans, transmitted to a receiving system at the destination that uses this information to synthesize and grow the encoded individuals, would require far less data than full mind uploading, while still achieving the transmission of specific human genetic identities across interstellar distances. This approach, sometimes called directed panspermia or digital embryo transmission, is speculative but physically conceivable. It would require a receiving system at the destination capable of synthesizing biological organisms from transmitted instructions, a robotic infrastructure that would need to be established before or simultaneously with the transmission. It raises its own profound ethical questions about the nature of the individuals created in this way. These approaches represent the boundary between science and genuine scientific speculation. They cannot be dismissed as physically impossible. They do not require faster-than-light travel or exotic matter, but they require technological capabilities so far beyond what exists today that they cannot be meaningfully planned for within any current engineering framework. Before asking whether humans can travel to the nearest stars, it is worth asking a more modest question, one with a more achievable answer. Can we communicate with the nearest stars? Can we send signals and receive them? Even if the round-trip communication time of approximately 8 years prevents anything resembling conversation? Radio communication across 4 light years is technically within reach of current and near-future technology. The Square Kilometre Array, a radio telescope under construction in South Africa and Australia, using thousands of individual antennas spread across vast areas to achieve extraordinary sensitivity, will be capable of detecting radio signals from nearby stellar systems with signal strengths comparable to what current radar systems emit. The question of whether there is anyone at the nearest stars to receive our transmissions, or whether there are any artificial radio signals coming from those stars for us to detect, is the substance of the search for extraterrestrial intelligence SETI program. Decades of listening have produced no confirmed detection, including from the Alpha Centauri system, but communication across 4 light years with confirmed recipients would be scientifically extraordinary, even with the 8-year round-trip delay. A dialogue, question and response, would take 16 years to complete one exchange. This is slow, but not meaningless. Scientific information, artistic works, mathematical theorems, technological specifications, anything that can be encoded as information could be transmitted. The nature of the exchange would be nothing like a conversation. It would be more like an exchange of letters between correspondents who must wait 8 years for a reply. Laser communication, using tightly focused laser beams to transmit information, offers advantages over radio for interstellar distances. A laser beam maintains its coherence over much larger distances before diffraction spreads it to undetectable density, and the information density per unit of transmitted power can be higher than radio. Laser-based SETI searches looking for artificial light pulses from nearby stars have been conducted and are ongoing. For the nearest stars, the communication problem is not physically intractable. The speed of light is the fundamental limit. No information can cross 4 light years, faster than 4 years. But sending and receiving information across that distance, with sufficient transmitter power and receiver sensitivity, is a problem of engineering rather than physics. We have been exploring the distance between here and the nearest star as a physical and engineering challenge, but it is also a philosophical one. The scale of interstellar distances has direct implications for one of the deepest questions in science, the Fermi paradox. Enrico Fermi's famous question, "Where is everybody?" is given particular force by the combination of the abundance of potentially habitable worlds and the age of the galaxy. If even a small fraction of the galaxy's billions of potentially habitable planets produces technological civilizations, and if those civilizations have any inclinations to expand or to communicate, then the galaxy should be by now filled with the evidence of their presence, and it is not. The radio spectrum is quiet. No alien megastructures have been detected. No visitors have arrived. One resolution to this paradox is precisely the interstellar distances we have been exploring tonight. Even if civilizations are common in the galaxy, the distances between them are so vast that colonization, even at velocities that seem rapid by our current standards, is an extraordinarily slow process. At 1% of the speed of light, the colonization wavefront of an expanding civilization moves at approximately 1 light-year per 100 years. For this wavefront to cross the Milky Way's 100,000 light-year diameter, it would require 10 million years. 10 million years is a long time, but the galaxy is 13 billion years old. If any civilization began this expansion more than 10 million years ago, the entire galaxy should have been colonized before our sun was born. The interstellar distances, then, are not sufficient by themselves to explain the Fermi paradox. They make expansion slow, but not slow enough, given the galaxy's age, to explain why no evidence of ancient expansion is visible. What the distances do explain is the absence of interstellar communication within any historically recent period. If the average separation between civilizations is hundreds of light years, consistent with the silence so far, then any exchange of messages would take centuries to millennia. Civilizations might exist at modest cosmic distances and never have exchanged a single message detectable with our current instruments simply because the light speed delay makes meaningful communication between distant civilizations a project measured in geological time. The vastness of interstellar distances thus contributes to the Fermi paradox not by making civilizations impossible to contact, but by making the timescale of contact so long that it has perhaps simply not yet occurred. Even if civilizations are common, the universe may be full of minds that have never met, separated by distances that make meeting impractical even across geological time. Throughout this exploration, we have encountered a consistent pattern. Every approach to crossing interstellar distances, every propulsion concept, every communication strategy, every alternative to physical travel, runs up against limits that are not technological but physical. The speed of light, the rocket equation, the vast energy requirements, the timescales that exceed human lifespans by orders of magnitude. These limits are not failures of engineering. They are features of the universe's physics. And as features of physics, they carry a particular kind of significance. They are, in a profound sense, non-negotiable. The universe is structured such that the nearest stars are genuinely, physically, nearly unreachably far from us. What does this teach? One lesson is humility. The universe was not designed for our convenience. It does not arrange its scales to accommodate human ambitions or human lifespans. The stars are as far as they are because the physics that produces stars also produces the stellar separations we observe. Not as a coincidence or a cruelty, but as a structural consequence of hydrogen gas, nuclear fusion, and galactic dynamics. The universe's indifference to our desire to cross its distances is not personal. It is simply physics. Another lesson is perspective. From within the narrow context of human daily life, where 100 kilometers is a long drive, where 10 years is a substantial fraction of a career, the distances between stars are literally incomprehensible. But from the perspective of the universe itself, which operates on scales of billions of light years and billions of years, 4 light years to the nearest star is nearly nothing. The Milky Way is 25,000 light years to its center. The nearest large galaxy is 2.5 million light years. The observable universe is 46 billion light years in radius. In this context, the nearest star is intimately close, and yet for us, it might as well be on the other side of existence. This gap between the cosmic intimacy of the nearest stars and their practical inaccessibility by human means is itself a profound statement about where we are. We are creatures of one world in a universe of trillions. We have developed the curiosity and the instruments to know about those other worlds, to detect planets around them, to measure the chemistry of their atmospheres, to understand the physics of what it would take to reach them. But we live, and very likely will continue to live for the foreseeable future, at the bottom of one particular gravity well, sending our instruments and our signals outward into a darkness that mostly does not return an answer. There is something clarifying in this, not discouraging, clarifying. The distance between here and the nearest star is a lesson in what we are and what the universe is. We are small and the universe is large. We are brief and the universe is ancient. We are here and the nearest star is 40 trillion kilometers away. These facts are worth knowing. They are, in their way, the most honest description available of our actual situation in the cosmos. The interstellar distance that we have spent this evening contemplating is not merely a constraint. It is also an aspiration, the clearest, most concrete, most physically defined goal that the long-term future of human civilization can point toward. There is something remarkable about the specificity of the goal. We know exactly how far it is. We know exactly what the destination contains, at least approximately, with more precision coming from Webb's observations and future instruments. We know exactly what the physics allows and prohibits. We know in outline what engineering approaches might eventually succeed. The distance to the nearest star is not a mystery. It is a challenge with defined parameters, and defined challenges, however formidable, invite specific responses. The Breakthrough Starshot Initiative represents one such response, an attempt to solve the problem of interstellar reconnaissance, if not crewed travel, within a generation or two, using known physics and foreseeable technology. Whether it succeeds is uncertain. Whether the specific approach of gram-scale laser sail probes is the right one is uncertain. But the attempt represents something important, the recognition that defined challenges invite defined responses, and that the scale of a challenge is not by itself a reason to stop working on it. The long-term trajectory of human space exploration, from Sputnik in 1957 to the Moon in 1969 to the International Space Station, to the planned return to the Moon and eventual crewed Mars missions, shows a consistent pattern of extending reach over time. Each step seemed impossible from 2 steps before it. The specific step to the nearest star is orders of magnitude larger than any previous step, and it may require forms of technology not yet invented. But the pattern of reaching further suggests that the direction of travel is consistent even when the destination seems impossibly remote. What humanity will do in the next 1,000 years, or 10,000, is unknowable. The technologies available in a century are not predictable from here. The social and political structures of a civilization a millennium hence are beyond imagination. Whether the species that eventually grapples seriously with interstellar travel will be recognizably human, or whether it will be something that emerged from humans but has been changed by time and technology into something different. These are not answerable questions. What can be said is that the nearest star is there. It will remain there. The physics that makes it difficult to reach will remain the same. And the desire, the ancient, persistent human desire to know what lies beyond the next horizon, will presumably also remain. The distance between here and the nearest star is 40 trillion kilometers. It is approximately 4.2 light years. It is 78,000 years at our current best speed. It is enormous and genuine and real, and it will, in whatever time the future provides, continue to be looked at from here, by minds curious enough to face honestly what they cannot yet cross. Tonight, while you listen to these words, Proxima Centauri is approximately 40 trillion kilometers away. The light leaving that small red star right now, at this moment, will travel at 300,000 kilometers per second through the interstellar medium for 4 years, 2 months, and several days before it reaches the vicinity of Earth. The photons completing that journey tonight left Proxima approximately 4 years ago. Between here and there is the interstellar medium, extraordinarily thin, extraordinarily cold, permeated by cosmic rays, and threaded by magnetic fields too weak to measure without sensitive instruments. It is not nothing, but it is closer to nothing than anything else the universe contains. No human-made object is heading toward Proxima Centauri. Our fastest spacecraft, moving in a different direction, would not arrive for 78,000 years if it were aimed there. The physics that would allow us to make the crossing in a human lifetime, at significant fractions of the speed of light, requires energy and engineering beyond anything we have demonstrated, and yet, we know it is there. We have characterized its star. We know Proxima has a planet in its habitable zone, detected by the gravitational wobble it induces in its star's motion. We have measured the star's age and mass and luminosity. We have spectra of its surface temperature. We have detected its flares. We have characterized in some detail the conditions that any planet around it must contend with. From 40 trillion kilometers away, using instruments orbiting our own planet, we have learned this much about a star we cannot visit. This is not nothing. It is in fact extraordinary. It is the power of science to extend the reach of understanding far beyond the reach of bodies. The instruments we build are not merely tools. They are extensions of perception into regions where perception has no other access. They allow minds formed on one small world to know, in meaningful detail, what exists at the nearest stellar system. The distance between here and the nearest star is genuinely vast, vaster than any comparison can fully convey. It is worse than you might have thought, more real, more physical, more grounded in immovable laws than the word distance usually implies. But it is a defined distance, a measured distance, a distance that physics describes with precision, and that engineering, over whatever time the future provides, may one day learn to cross. For tonight the distance remains. 40 trillion kilometers of cold interstellar space, populated by a hydrogen atom per cubic centimeter, and threaded by ancient cosmic rays. Between us and the nearest star, between this moment and whatever understanding the future will bring, it is vast, it is real, it is patient, and we, briefly, curiously, stubbornly, are here at one end of it, looking. Thank you for spending this long, quiet evening with us at the edge of what is reachable, for sitting with the skull of what separates us from even our nearest stellar neighbor, not with despair, but with the honest, grounded wonder that genuinely understanding a thing's difficulty provides. The nearest star is 40 trillion kilometers away. We know it is there. That is where we are.